dependency graph like this one. So you have one thread that waits on some resource, a mutex, most likely. The mutex is held by a different thread, which waits on another mutex, which is held by the first one. So this is the simplest circular dependency, where you have two threads and two mutexes held like this. But you can have a more complex dependency, circular dependency case. You can have 3 or more threads. So as long as you have a circular dependency, you get a deadlock. You can also have somewhat different cases. So with mutexes, it's the easiest case of such dependency. But you can have dependency where you have a thread waiting for another thread to finish, so executing join. Join is a direct dependency between threads. You will have an arrow, let's say if P calls join on Q, you will have an arrow going from P to Q. So P waits on Q directly. And if Q waits on mutex held by P at that time, you have an even shorter cycle in such a dependency graph. And I encountered this kind of bugs in real programs. So typically when you wait for another thread to finish, so you execute a join on another thread, you shouldn't be holding mutexes. Or if you do hold mutexes, you must make sure that none of them can be of interest for the thread you are waiting for to finish, so that you don't end up in such a dependency. And we'll see about condition variables as well, that you can end up with deadlocks. What to do if you are in a potential deadlock situation? There are two strategies. One of them is, yes?
I wanted to say that we can kill one of the threads.
Sorry?
We can try to kill one of the threads. If we see that something like this happens, like two threads are just sitting there and waiting, we can probably just kill one of them, and that will release one of the resources.
Well, yes, you can escape a deadlock by killing a thread, but it's problematic to go on this approach because you don't know what's the state of the data when you kill a thread. So you will end up most likely in some data inconsistency. Let's go to the example here. Let's say I'm doing this way of transferring the money, and a transfer deadlocks when it tries to acquire this mutex. Now, if we kill the transfer at this moment, the problem is that the balance on the source account is updated and the balance of the destination account is not updated. So it's a no-go. That's, by the way, why forcefully terminating a thread is generally not a good idea. Now, what are the solutions? One of them is indeed inspired from this killing a thread, but you won't kill the thread you will somehow signal that thread, or the thread itself will realize that there is a potential problem and back up. Because the thread knows what it was doing and how to roll back what it already did. That's one possible approach. So you use that function try lock. So let's go, I guess it was here. So I'm trying to do the transfer, and I discovered that so here I'm trying to lock the destination, and I have the function try lock, which fails if the mutex is already locked. So if I fail to lock here, now the destination is unlocked, the source is locked, but I can back up. So I will say, I'll revert this statement. So source balance plus equals amount. I put back the money in the source account. And then I will unlock the source mutex and return false. So I failed the transaction. That would be one approach, and let the caller deal with the mess that I'm leaving. By the way, in case you wonder why see, do I get directly? Why do we have compare and exchange weak and compare and exchange strong? Why do we have these pairs of functions? So compare and exchange, both of them compare the current value of the atomic variable with the expected value. And if they are equal, then it assigns the desired value to the atomic variable and returns true. Otherwise, it returns false. Now, compare and exchange weak, if you look at the documentation, it says something like it can fail spuriously. It's possible comparison yields equality. Why having comparing the exchange weak? Because possibly situations like this one, like the one here. So if the compare and exchange interferes with some other operations, let's say you have two compare and exchange operations on the same variables, on the same variable performed on different threads, they may interfere in a way in which both of them fail. So in this case, if you call compare and exchange weak, both threads will see that as a failure. Now, both in case of compare and exchange weak and in case of this transfer, the caller could try again after the operation failed. So imagine that you put the transfer in kind of a loop until it succeeds. Now, of course, you may want to know why it failed, because if it failed because you don't have enough money, then it's unlikely to succeed if you try it again quickly. You may have to wait for a month or so to get a salary and attempt the transfer later. But yes, you can put this part of the code into some kind of a loop. I won't go into the details, but you can imagine how to change the code so that if we fail because of this, then we simply try again. So this is one possible solution. When implementing this kind of a solution, as I stated earlier with what if I loop even if I don't have enough money, you have to be a bit careful not to end up with what's called a live lock. Actually, you have two problems. The possibility of a live lock, so you go from here up to the point you give up, and try again and try again, especially if you have two threads that are doing the same and for some reason they get in sync. There was a similar problem. Now it's a hardware one. In the beginning of the Ethernet networks. So originally the Ethernet networks had a single shared cable, shared communication medium, and all the computers on that cable could send messages. So if a computer decides to send a message, it listens for other messages from other computers, and if it's silent, then the computer will send the message. But the computer will also listen for other messages, and if it detects that another message has been sent in the same time, it gives up, sends something to signal that there was a collision between the messages, and tries again after a while. Now, of course, the other computer that sent the other message will do the same. And if the time until the repetition is the same for both computers, it's very likely that they will collide again and again and again. And for that reason, the delay is randomized, so that it is unlikely that a collision happens again and again and again. In programming, we will call such a repeated collision a live lock. And the solution here and there as well is to wait for a random amount of time. Speaking of waiting, if you put this in a tight loop, so without having a sleep call or something similar, then we end up with consuming a lot of CPU power. If we put a sleep, we have two problems. So first of all, the sleep must be something randomized a little bit in order not to repeat each time the collision. Now, hopefully, if the section from here to here is short and quick, and the waiting time is way longer than that, the probability that you get exactly the same collision over and over will decrease. But again, a bit of care is needed. And the other dilemma when doing sleeps in your programs is how long to sleep. By the way, sleeping in a program, in a concurrent program, is usually a code smell. And there is a big issue with how much should you sleep. If you sleep for too short a period of time, then you consume a lot of CPU. because you execute the loop very often. If, on the other hand, you sleep too long, the program becomes unresponsive. Let's say you wait for a few milliseconds. Well, a few milliseconds for a human is a short time. A few milliseconds for a computer that executes a few billion instructions per second, it's a very long time. It could execute millions of instructions during that time. So when you start putting sleeps, then you open a big can of worms. The other solution to this deadlock problem is to make sure that they never happen, that you will never end up with a circular dependency. And one of them is to, how to do that is to sort the mutexes in an arbitrary order, it doesn't matter. But when taking the mutexes, you will take them only in that order. So again, with our example here, you put an ID on each account, say like this, and this is a constant. Of course, I will get some errors because I don't have a constructor. And the code will be something like if source ID less than the destination ID, then I lock first the source and then the destination. And the unlocking goes in a different way. So the rest of the code will look a bit different. But anyway, and if they are in the reverse order, then I will lock them in reverse. So always I lock the accounts in increasing order of their IDs. The audit function will have to do the same. So again, parse the accounts in increasing order of their IDs and lock them. And in that way, you are sure not to have such circular dependency. Because if A comes before B, then it's possible that Q holds A and tries to acquire B, so it waits on B to be released, but P cannot exist in this place because P already holds mutex B and is trying to acquire mutex A. And that's forbidden by our rule that mutexes are to be acquired in increasing order of their IDs. So P should not do what it is doing. And if the mutexes are always taken in increasing order, then any process will put a dependency only in the forward direction between the mutexes, and this means you will never end up with a cycle. An extreme case of this rule of always acquiring the mutexes in increasing order of their IDs is to never acquire a second mutex. So never hold two mutexes at the same time. Never try to acquire a mutex while holding another one. And then you trivially obey this rule for whatever order of the mutex is. So that would be a second approach. Now, with this approach, the good thing is that you don't have to back up. You have the certainty that you will do the operations. The downside is that it's hard in a big program to control the order of acquiring the mutexes. Because in a big program, you will have multiple modules with multiple mutexes, lots of objects with dependencies in all directions, and it's a bit hard to make a discipline that all parts of your program obey. Although this may be linked with issues like if you have a big program and there is some event happening and this changes variables or objects throughout the whole program. What are the intermediate states? And this is a non-trivial problem. Anyway. And another thing on mutexes before moving on, recursive mutexes. You encounter them in languages like C# and Java. You only have recursive mutexes. So what is the issue? The issue is what happens if a thread holds a mutex and it tries a second lock operation on the same mutex. So if you attempt a lock operation on a mutex that is already locked by the same thread. Now, with pthread mutexes, you probably discussed about, I guess there were 3 types of mutexes. The basic ones, the recursive ones, and I don't remember checked mutexes, if I remember correctly. So for the basic mutex, it's undefined what happens if a thread tries to lock a mutex that's already held by the same thread. With checked mutexes, you fail to lock. Try lock would return probably false, and a lock, I don't remember. It triggers an assert or something. By the way, that's what typically happens in C++ in debug mode. And the recursive mutex can be acquired, but if you acquire the same mutex a second time, you will have to release it 2 times in order for it to become free and to be usable for other threads. With the standard mutexes, and this is the most likely thing to happen in C++, is that you get a deadlock. The system sees that the mutex is already taken and the thread is put to wait. And of course, it will never advance because the mutex is held by the same thread, so it will never get unlocked. Now, recursive mutexes, if you look a little bit, lots of people say that it's a bad practice to use or to rely at least on recursive mutexes. Now, what are the issues? And I guess I'm lacking an example here, so I will create a new, or I will put here as well. The basic case you need a recursive mutex comes in handy if you have something like this, a class. Let's say C, I don't care much. And you have 2 functions that does something. and another function that again does something, but at a certain point it calls f. Now both of them will need exclusive access. So I'll have a mutex here. So f will start by saying lock will do something, then unlock. And G also needs some access to the private variables, so it will start by saying lock, and in the end, it, let's say, does something else here, so it will do unlock. And this is a use case for a recursive mutex, because with a standard mutex, you will get in trouble. The mutex is locked here, then we call f, and f will try to lock the mutex again. Now, this kind of a problem has a very easy solution that does not use recursive locks. But before that, let's notice something, and this is the issue why recursive mutexes are frowned upon. When I'm entering the function f, what's the state of the private variables that are here? Are they coherent? Are the class invariants obeyed when I'm entering the function f? And the answer is it depends. If f is called from the outside, then yes, I'm acquiring the mutex, the class mutex here, and I'm sure that the invariants of the class are obeyed in that case. If f is called from G, then the invariants may be not obeyed, because G could have changed something here. So, and this problem with what invariants you can rely upon when acquiring a mutex and what invariants you cannot rely upon because the mutex may have been already taken by your current thread, by caller somewhere up the stack. So this problem is even more complex if you have a more complex code. So instead of relying on recursive mutexes for simple cases like this and potentially running into trouble when the code becomes more complicated, a better solution is to ditch them completely and refactor a little bit the code. And the solution here is to define a private version of f that now is called, being private, it cannot be called from the outside, and we can make a rule that f is always called under the mutex. So then f and everything that f is doing gets moved here. So the public f simply calls the private f. And then G, when it needs some services from f, it will call the private version of f. And now we don't need recursive mutexes, and we also have better control on the invariants. So now all the public functions know that the class invariants are satisfied on entry, or rather at the time they take the class mutex. And the private function, we have to be careful what are the properties, what invariants hold and what invariants do not hold. But we know that it's always called from member functions, and we know all the places where it is called, and we can put here a comment saying that such and such invariants are guaranteed to hold and the others may not hold. So roughly this would conclude the discussion on mutexes. I guess we also had a short discussion on read-write mutexes, also called shared mutexes. And the problem behind that. So very shortly, you have some readers that don't change the data and some writers that do change the data, and the writers are incompatible with each other, but the readers are compatible with other readers because readers don't change anything. So generally speaking, you may have any number of readers at the same time without any issues. So then you have a mutex that can be locked in two modes, in read mode or shared mode, or in exclusive mode or write mode. And the mutex must make sure that those rules are obeyed. And here is a note on the implementation, and it's important to understand what's the behavior. So what if we have several readers holding the mutex? Now a writer comes in and tries to lock the mutex. It's impossible, so it will be put on wait. And now a new reader comes in. Do you give him the mutex or not? It's possible to give the mutex because it's held in shared mode, but if you give the mutex, you run the risk of starving the writer. If you always have readers that come in. And one more thing. You can lock the mutexes with lock and call unlock when you are done, or you can use the so-called resource acquisition is initialization way of doing the things, and then you put unique lock or guard lock. Unique lock, this is a template over the mutex type. And then you don't need the lock and unlock. The constructor of this object takes the mutex as an argument and locks the mutex, and the destructor, which will be called on exiting the block, will unlock the mutex. The advantage of using unique locks is that it's much easier to make sure you don't forget to unlock the mutex. Especially if you have functions with multiple returns, or you have functions with which can throw exceptions. If you have a unique lock, whichever way the block is exited, you are sure that the mutex is unlocked at the end. By the way, with exceptions, you must also make sure that when you exit because of an exception, all the invariants are reestablished before releasing the mutex. So it's not for free, but well, you can do that. The unique lock, unlike the guard lock, guard lock, so maybe the guard lock is preferably to be used. So a unique lock can be released. You can say the lock object unlock, and you can lock it if you need at a later time. If by the end it's unlocked, so the unique lock object knows if the underlying mutex has been locked by it or not. So if you unlock it and you don't lock it again, then the destructor will do nothing. Now, of course, when using lock objects and unlocking them somewhere in the middle, you must be careful and understand that it's not from the beginning to the end that the mutex is locked. So it's unlocked from here to here. So from here to here, anything may happen. So another thread may come and do something that, well, it's not otherwise allowed. But it's generally a good idea to use this resource acquisition is initialization technique and to use this mutexes, lock guards or unique locks over the mutexes, because it makes the code much more readable and much easier to write without forgetting things and making bugs. By the way, especially if you have an exit route from the function, let's say a return, that's seldom used. That's very likely to not be covered by the existing tests. So with a unique lock, it's easy, the mutex will be unlocked. With the other case, possibly you forget the unlock and you don't discover in your tests. Java and C# languages have the lock block. So you can do something like you have, okay, let's say I put here a static. This, and if I remember correctly, the way to go here is to say lock of lock object, or let's say it's a mutex, actually it's not a lock, like this, and you can say something like this if you need. It's a silly example, but this cannot be unlocked in the meanwhile. But you have also the classical mutexes as well, with the possibility to lock and unlock. Okay, and now for the producer-consumer problem and using condition variables for that. So there are two basic problems in concurrent programming. One of them is you have two threads that have to concurrently access a resource, and we have to protect concurrent access so that they don't step on each other's toes. The other problem is you have a thread doing something and another thread needing that something as input, using that something as input. And the basic way of doing that is something that's called a condition variable, which is a misnomer. It's a complete misnomer. It's not a variable, and it doesn't hold any condition. But this is the name that was chosen, and that's it. Here you have also the basic example you encounter probably in other places as well. It's a very versatile basic primitive, but as any primitive, it's hard to use. So let's see what are the things. So you have a producer thread that produces something, puts it in a variable that's accessible to the consumer thread. This is the local computation. And now it locks a mutex that's also used by the consumer. It puts the result. It marks in a global variable that the result is ready, and then notifies the consumer thread or threads. Now, the consumer, what it does, it has to lock a mutex. We'll come to that a bit later. The basic part is this one. It has to wait until the ready variable from here gets set on true. Now, with atomic variables, you can solve this problem by simply having here a spin loop. But as I said earlier, the spin loop is expensive on the CPU side if this thread takes a while. And imagine you have only those two threads in your system, and the consumer consumes CPU for nothing, while the producer thread will need that CPU power in order to do its job. So we use this condition variable to send a notification from here to here and allow the consumer to actually wait releasing the CPU. So behind this wait, it's a call to the operating system, and the operating system will realize that the consumer thread has nothing important, nothing useful to do. And so the consumer thread can be put to sleep until this condition variable is signaled. So that would be the basic stuff. The producer notifies, and at that time, the consumer wakes up and continues the execution. Now, the complicated part is that we have to cover for race conditions. And in order to make it very versatile, the condition variable, as I said, it's not a variable. It doesn't have a state. It's a kind of a communication channel, rather. When somebody calls notify on a condition variable, all the threads that are waiting on that condition variable are woken up. And that's it. A thread that calls wait at a later time will lose the notification. The notification is transient. It happens and it goes away and it leaves no trace. That's why I think the name variable is inappropriate and misleading. But well, we have to deal with that. So we always will have something like this when using a condition variable. We will have the condition variable itself and something that allows the consumer to know that whatever it had to wait for is available. It may be a separate Boolean variable, or it may be the result itself. So the consumer will do a loop where it will execute wait until the result is available. But this raises a potential race condition. What happens if the consumer goes here, finds ready on false, but between this moment and the moment it goes to execute the wait instruction, the producer goes through here, so sets ready on true and executes notify.
That's why we have the mutex.
That's why we have the mutex, indeed. So the producer will hold the mutex during that time, and the consumer will also hold the mutex that time.
Basically, the mutex in a condition variable is to protect the actual condition, like the ready variable, right?
The ready variable together with the wait.
Yeah.
Yes, that's very correct. Now, if we simply put a mutex here, we run into a deadlock because waiting while holding the mutex will not allow the producer to enter here and notify. So this is why the wait statement has the mutex as an argument, and it releases the mutex for the time the waiting is taking place, and reacquires the mutex afterwards. And in C++, you need to use a unique lock object to hold the actual mutex, and to pass the unique hold object to the wait call. So it atomically releases the mutex and goes to sleep, so that nobody can notify or enter here and do the notification, and we lose the notification. So if we know that the notification hasn't happened before, we know that we won't lose it while waiting. So we can go to sleep and we are sure to receive the notification. Now, how to use such a thing into a more complex example? A typical thing that you need is, let's see, what if you have a thread computing something and another thread consuming the same thing? Then you need, I will another example here, something that is very similar to what we are going to discuss next, futures. So let's call it future. And let's make it more clear. It's a template over some type T. So I have two public functions here. One of them is get, that, and another is set. So the idea will be the producer, well, the future is shared between the producer and the consumer, is a global variable. Let me put here some sample code. So have the producer, we have, let's go, move them here. We have something like this. So the producer at some point we'll do some computations, and at some point we'll call fset with the value computed. Let's say it computes the answer and it sets the answer to the future. The consumer will maybe do something before so that we have some parallelism, and we'll get the value from the producer and we'll do something with the value. So this would be a typical thing to do. We have a function that produces something, and then the consumer or consumers consume the value that is computed by the producer. You can imagine a more complex scenario where you have multiple producers running in parallel and setting the result in multiple futures, and then the consumer gathering the results from all the futures and doing some computation that needs all those results. So imagine, for instance, I have a big vector. I have several producer threads, that compute the sums of some parts of the vector. And then and they run in parallel, and then a final thread that gathers the partial sums and sums them up to find the sum of all the elements in the whole vector. Now, how do we implement such a thing? So essentially, it's a one-shot event. In the beginning, the future is uninitialized, has no computed value, has no value. Then set can be called exactly once, only once, and it will wake up all the threads stuck in a get and will give them the values. So we need a bool is ready, initialized with false. We need a value. Now, of course, if you don't have a default constructor on T, you need a bit more work, but that's another stuff. You need a mutex. And we need a condition variable. And now set is very similar to the example that we have here. So we need, I guess I will copy paste this. X. Now this will be, we copy the parameter, is ready becomes true, and we notify the condition variable. And essentially that's it. The consumer, again, it's something like this. So we acquire the mutex, and while is ready is on false, we wait on the condition variable and unlocking the mutex. And here we return mval. And that's it. So the producer will go to set and will set the value in this local variable and will toggle, will set the is ready on true, and then it will wake up any waiting thread, any consumer. Now get goes here and logs the mutex, checks is ready. If is ready is already on true, so if we come after set, then we skip everything here and we return the value. If is ready is not yet true, then we wait. If we go to wait, we unlock the mutex and we wait for the producer to come in here and set is ready on true and notify everyone. Now, there are a few more details here. You don't have a function called notify. You have a notify one and a notify all. And there's a reason for that. And the reason is related to optimality of the code. For the time being, I only say that here what we need is a notify all, because we need to wake up all the threads. If you have multiple consumers, we need to wake up all of them because the information needed is available for all the consumers. It's the same thing in all cases. So for all the consumers. Another use case, and by the way, this is why the condition variable is not actually a variable. The idea is that we can reuse a condition variable. We can have it send several notifications. So in this case, we have a single notification happening. Set is called a single time. But we have another use case, and I leave a large part of it as an exercise. What if I want a queue? So on the public side, I want an in queue and I want a dequeue function. They are similar to what we have here, but now they will happen several times, not a single one, a single time. And I don't go into writing here. Here you have an example of how to implement this and also use case. So this is a larger example with several threads. Producer that produces some numbers and enqueues them into a queue. And second one that takes from the queue, sums up the elements, and at the end we'll talk a little bit about what happens, what does it mean to be at the end. It enqueues in the second queue, and a printer that takes from the second queue and prints what comes in. And here is the main that creates a bunch of threads. Now, enqueue is quite easy to implement. So let's see what we have here. We have a mutex, we have a condition variable, and we have the basic queue that is not synchronized. This is provided by the standard library. So the enqueue is simple, locks the mutex, pushes the value into the non-thread safe queue, and we'll discuss a bit why we have a notify one here. Now, for the dequeue function, you can notice that what I sketched here is different from what I have here in the complete example. And when you have something that goes repeatedly, one problem to solve is what happens at the end, or to design what happens at the end. So how we end up the process. We have a producer that produces things and puts them in the queue, and the consumer that takes objects from the queue. Now, somehow the consumer must know when the elements are finished, when the producer finishes the elements. Now, it may have its own way of finding out, but sometimes it's not possible to have such a thing. So let's say you have some commands, let's say some transactions that are put into a queue, and you have several worker threads that process those transactions. And then all those workers will execute the dequeue function. Will be in a loop where they dequeue an order, something to do, and then they will execute that thing. And then repeat the loop and dequeue the next element and so on. So there's no way of knowing when there are no more elements. If you have a single consumer, it's easier because with a single consumer, the consumer may keep track of what happens and somehow determine that, well, this was the last object to be processed and now I'm done. So we need also a way to signal the end of the stuff. And it's not the only design possible, but here is a way. We have a close function that notifies all the consumers that there will be no more elements in the queue. So the producers somehow agree that there are no more elements, and one of them will call close to signal that there are no more things to be done. And somehow the consumer will need to know that there will be no more elements coming in. And one possible design is that dequeue returns an optional. It's something defined in C++, I guess 17. An optional may have a value of this type or may have no value. And someone receiving this can check. And here is how the intermediate, the adder, works. It performs a dequeue in X. If X has no value, we are at the end, so we exit the while loop. Otherwise, we use the value. And by the way, the optional has the syntax like for a pointer. So star X is the value held by X, the value of type int in this case. So the adder, what does it do? It takes elements from the queue. It adds them up, and when the queue is empty, it gets here, it writes in the second queue the sum that was computed, and that's it. And if I remember correctly, the program is like this. You have a producer that writes into a queue. You have a number of adders competing for the elements in that queue. Let's see. We have the printer, it started first. The producer is last and will write in the first queue. And we have a number of adders that take from the first queue and output in the second queue. So the adders will compete over the elements put in the queue by the producer. We'll add up them. And when the producer closes the queue, the adders will consume all the remaining elements and will write the results into the output queue. And finally, the printer will take from the output queue a number of numbers equal to the number of adders. So we know that X has to have a value. It sums up those partial sums and prints the result. Okay, so question is, how do we do that? In addition to the queue itself, we need a Boolean telling that we are done, that close has been signaled. And close locks the mutex, sets isEnd on true, and here we have a notify all. I'll come back to that. Now let's see the dequeue. We lock the mutex, and now the things are a bit more complex, so we'll put a while true loop here. Now, we have to decide what happens if the queue is not empty and isEnd is signaled. And as I said, we want to consume all the remaining elements. So in this case, the priority is that the queue is not empty. So if the queue is not empty, even if isEnd is signaled, we return the element from the top of the queue. Only when the queue is empty, isEnd is used. By the way, this queue looks a lot like FIFO or a pipe, a Unix pipe. We have producers that write bytes in the FIFO or in the pipe, consumers that read, and if the writing end of the pipe or of the FIFO is closed, then the consumers will read any remaining bytes, and then a read will return 0 bytes read, which signals the end of the data. So if we have at least one element in the queue, we pick it up and we return it. By the way, this is C++ style. We can find out what's the element in the front, and we can pop it to remove it. So front returns the element without removing. Pop removes the element without returning. That's because of some exception safety issues. What happens if the assignment here throws an exception? But that's another story. Now, if we reach here, it means that the queue was empty. So now if isEnd is on true, we return an empty optional. And if we reach here, it means isEnd is on false and the queue is empty. So we have to wait either for a close call or for an in-queue call from a producer. So we do await releasing the mutex that was taken here. By the way, it's very convenient to have such a thing and not have to unlock the mutex here and here before the return. Also notice that I'm holding the mutex while verifying the queue, while verifying this variable and so on, while modifying the queue. So this is also for the purpose of protecting the data, the full data in the producer-consumer queue. So that would be the example. As you can see, the condition variable is notified multiple times, once for each element in queued, plus once for closing. So that's why the notification is transient, and it's not a simple variable that becomes true when you notify it. And you can construct more complex objects like this producer-consumer queue, which are much more convenient to be directly used in the application. This one or the future earlier. Now, one more thing regarding this notify one. Notify all is always safe, but notify one is more efficient where it is correct to be used. Now, what's the issue with that? Imagine you have several consumers. Let's say you have 10 consumers, and all of them execute a DQ, and all of them will end up here because the queue is empty. Now comes a producer, a single producer, and enqueues one element. So push the element there, the queue is of size 1, and notifies the consumers. Now all the consumers wake up, and remember that when returning from wait, the mutex is reacquired. So this means that only one of the consumers will acquire the mutex and repeat the loop. All the others are still in the wait, but they are waiting on the mutex to be reacquired instead of waiting on the condition. Now, the first one will find a non-empty queue and return the element. Now, the second one wakes up, acquires the mutex and gets here, only to find an empty queue, so it will return here, releasing the mutex so that the next consumer can wake up and repeat the loop and end up here. So we will have one consumer retrieving the unique element from the queue and returning, and all the other 9 executing this loop for nothing. And for this reason, we have this notify one that moves a single consumer waiting in the wait from waiting on the condition variable to waiting on the mutex. So this is why we did it this way. So, well, that would be for today. We'll continue next time with these higher level concepts. So thank you. If you have questions, please ask. Otherwise, see you next time. Bye.
Have a nice day.
Have a nice day. Bye.